All right, so no one is online. Wow, that's pretty good. So that means everybody's in class. Okay. So I'm going to close the door and let's just take attendance. And are you happy with the camera angle? Should I turn like this? No. Okay. All right, so let me just to take attendance.
I can move that way. Just gotta make sure everything's on.
We gotta get away from Spider-Man.
I just want So I can.
What speed is the podium? Your laptop?
This is not.
Okay.
I'm not. Okay. Okay. Paper up, please. Zoe, Zach, Stefan, Robert, Heidi, Jacob, I'm working on memorizing this. Jacob, Cody. Peter, Anthony. Okay. Okay. Everybody is in class today. Nobody's online.
This is yours, right?
No, it's his.
Oh, is this yours, Professor?
Yep.
Okay.
Laptop is it, isn't it?
Yes.
This is yours.
Thank you.
I know this is yours. Okay, let me double check.
The world is broken.
Okay, good. So attendance done. So try not to forget to share my desktop because if I do, it's gonna be a nightmare. So now I'm sharing my desktop. Okay. And since nobody's online today, so I just basically care less about online components. But okay, so today we're going to do a bunch of things, quite important. So let's just continue going on A3. Wrong file, sorry. Okay. And I got, let's visit course homepage. Take a look at updates. Okay. I hope you received this update yesterday. No, Wednesday. Okay. So hopefully you're working on, first of all, quiz 0 problem 3.
Yeah.
And then you're working on quiz 3. It looks like a very similar question, but it's fundamentally very different. So you have to realize those things, okay? So this is the basic principle of how the wind tunnel operates in low speed. Now, low speed wind tunnel is governed by an equation. Of course, you know, we're gonna derive that equation today to begin with, okay? All right, so let me just open up one more. Okay, so where did I stop in last class?
The problem.
Momentum principle, right? So what did I do in last class? Somebody please tell me. Yeah, go ahead. You don't have to raise your hand.
We were talking about, I think, a converging duct and was using the momentum principle to determine whether or not we could actually use the A1, B1 equals A2, B2 equation.
So you got one equation at the end of last class. What is it? Euler's equation. So that's what we got. Okay. And then now you realize, hey, this is something we already exposed in fluid mechanics. We know that. Okay. So now I guess the question is, you probably never use Euler as is. You have to do something before you can actually pick up and use it to solve the problem. Right? Mm-hmm. Yeah, that is where confusion comes in. Okay. And let's just take a look at it. So in last class, we got this equation. This is called Euler's equation, and this is nothing new. You actually saw it in fluid mechanics. Now, in fluid mechanics, this equation comes from a concept of a streamline coordinate system. Streamline coordinate system. You're going to pick up one streamline as a coordinate. Then you're going to set this direction and that direction. Then you apply equation motion, which is Newton's second law of motion, F equal to ma in this direction and that direction. And then this direction, that direction comes up with certain kind of acceleration. This direction is a centrifugal acceleration that actually creating higher pressure. If that principle is applied for a centrifugal compressor, of course, you can compress air. Now, this direction is something we are going to talk about. This is called conservation linear momentum. And that actually leads you into the Euler's equation, which you are seeing here. So obviously, this is differential equation, first order. Okay, ordinary differential equation, first order. Oh, cool. So can I integrate to get something out? Not so. What is the problem by looking at this equation? Somebody please point out, hey, you know, if I'm given this kind of equation, here is some physical challenge I'm going to have. Well, this is ordinary, not the partial. Partial is tough. How can you integrate partial differential equation? Somebody please tell me that from your math knowledge. It's impossible. Sorry. Impossible to integrate partial differential equation. Right? Of course. Because this variable you want to integrate is a function of multiple things. That's why this is partial differential equation. How can you integrate such a thing? Impossible. Ah, too bad. Okay. So now you have to somehow, okay, change the partial into ordinary. Hey, this is ordinary. That's why we picked up streamline as a coordinate. The reason why we picked up streamline as a coordinate is we can express this inherently partial derivative into the ordinary differential equation as long as you stick with a streamline. Okay? That's the reason why this is an ordinary differential equation. But the condition is always we have to use this equation together with in the tangential direction of streamline. Oh my goodness, I took care of one headache away from you now. So what's next? Go ahead and integrate, right? Can you integrate this? Instantly, I realized, wait a second. I don't think I can integrate as is. What is it? Go ahead.
We could replace rho with the state equation.
Rho is function. B is function. even you constrain yourself in a direction along the streamline, tangential direction, both of them were constant. It's not a constant variable, so that's a constant. Sorry, variable. This is variable. This keeps changing. This is variable. It keeps changing. If you have two variables multiplied together, what kind of function you're going to get? It's a highly nonlinear function. If the function is highly nonlinear, you can never integrate. You have to linearize it somehow. What is your first idea to linearize this? Go ahead, Daryl. You probably have a good idea.
Density is
constant, yes. So that is the first idea of Bernoulli. Bernoulli is a student of Euler. And Euler said, okay, well, so this is the equation I invented. Go ahead, do something. Okay, well, as a graduate student, I have to do something. So Bernoulli did assumption. Okay, well, let's assume density constant, knowing that, hey, this is a terrible assumption. Who actually said the density is constant in there, but I have to do it because I cannot graduate, get a real job. I'm a graduate student of Professor Euler. He's a terrible guy, yelling at IT people. Yeah, but I have to somehow graduate, get a real job. I have two kids. You know, that was like back in 2001, my situation. But anyway, density, if this is constant, yeah, you can integrate. Density goes outside. You can finish up integral. Here we go. Let's talk about Bernoulli's equation. Okay. Next page. So you're going to pick up a streamline. So you see two different kinds of streamlines. This is a streamline 1. This is a streamline. So as long as you stay in the same streamline between position 1 to position 2, you can integrate Euler's equation between those two locations in a direction tangent to the path between 1 and 2, between 1 and 2. You can integrate, and if density is constant, goes outside of integral, you can finish up integral, you can get, oh, this is the equation I got. What is this? Bernoulli's equation. So it's essentially the same thing you went through in quiz 2, right? Between here and here, you try to integrate the hydrostatic equation. Then what did you get? Pressure difference.
Negative pressure.
Well, sometimes negative number if it's terribly different.
Something illegal.
Yeah, sometimes it fails. But same thing. This is a fluid dynamics coming from Euler's equation. Now you can integrate along a given streamline, then you can get the pressure difference. That is Bernoulli's equation. But what is the one constraint? Of course, density must be constant. Somebody please tell me the condition of density constant. Incompressible or low speed, you can say Mach number less than 0.3. That's right. This is incompressible subsonic flow. One important problem here, can you apply Bernoulli's equation casually between 1 and 3?
Nope.
No. How about 2 and 3?
No.
No. Why is that?
Different streamlines.
Those are different streamlines. You can never do such a thing. However, if you go really far away, can you apply between here and here? Because this point is now really far away right here. Point 1 is here. It almost seems like everything is starting from here and separate all of a sudden here. So that means between 1 and 3, possibly. It depends. It depends. In other words, this one is really far away from the presence of the body. What do you call that kind of flow? Free stream. Important idea. Free stream. Free stream. Repeat after me. Free stream. Here we go. Free stream. This is an important concept. This is actually coming from, terminology-wise, coming from wind tunnel testing. In other words, this is a wind tunnel test section airspeed, which is not affected by the presence of a test model. Ideally speaking, if this is infinitely far away from the presence of this body, it is called free stream. Oftentimes, infinity is associated with this. What is infinity? Because it's infinitely away from the presence of the actual model in the wind tunnel, ideally speaking. So this is undisturbed test section airspeed. It's called free stream of a wind tunnel. So free stream is an important concept, yet no one really probably explained to the detail in fluid mechanics. So today is the day. Once again, I'm going to sacrifice a little bit to go over fluid mechanics idea of Bernoulli's. So you guys get that? This is Bernoulli's equation, right?
Yes.
Now one term is completely missing here from fluid mechanics. What is the term?
Hydrostatic pressure.
Hydrostatic pressure difference is completely missing because air is, well, we no gravity. Okay? So if this is fluid mechanics version, gamma times z term is added. What's that? It's a hydrostatic pressure variation. It's a height. Well, we don't care about it. Okay? So now, another important aspect here is these are the limitations. In other words, assumptions built into the Euler's equation is already 3 of them. Steady flow, no body force, gravity 0, viscosity 0, imbecile, no boundary layer. That is Euler. Plus, on top of it, you're assuming density constant, incompressible. So lots of assumptions. Those are also at the same time limitations of using this equation. Okay. So let me just quickly move into the next page. Let's just start discussing using Bernoulli's equation to solve something real. Okay. So consider an aircraft wing in a flow of air, where far ahead upstream of the wing called a free stream. Here we go. The pressure, velocity, and density are measured as 1 atm absolute, 100 miles per hour, and 0.0024 slugs per cubic foot, respectively. At a given point A on the wing, the measured pressure is 2070 pounds per feet square. What is the velocity at point A? So how do you handle this? Go ahead.
You gotta assume. You gotta go through the Mach number.
Yeah.
Choose, and then from there.
So let me actually let the bird take care of it. So Ernie bird shows up. Okay. This is not the professor. Okay, just the bird. Ernie thinks. Okay. This is not the Dr. Age, it's Ernie. Or, you know. So this is a free stream, like you said, it's infinity. So pressure at that point, let's call pressure infinity. Plus density at that point, let's call density infinity. Velocity at that point, velocity square over 2 must be equal to pressure at location A plus density at, what's density? I don't know, density A, dA square over 2. I guess the big question is, what is density?
Density is constant.
Density is constant?
Yeah, density.
If we're going to use this equation.
Rho infinity is rho A, which is a given? Yeah. Let's use 0.0024 slugs. It's a nice standard unit. Cubic foot. Oh, okay. So Ernie says, I'm going to move on, compute BA. BA is square root. B infinity square plus 2 times P infinity minus PA over rho infinity or rho A, either way, because it's the same thing. Okay, and then if you plug that in, the values plug in. B infinity is 100 miles per hour. I'm going to convert it to standard units. What is it, standard units wise? You are going to 100 miles per hour multiplied by 88 feet per second, 60 miles per hour, which is 146.667 feet per second. Okay, so I'm going to plug in that 146.667 feet per second squared plus 2 times P infinity. Well, P infinity is what? It says 180. What's 180 m? Anybody?
216.8 pounds per foot square.
Well, you need to know the altitude though. So let's assume this is sea level. No one says so, but let's assume this is sea level. What is the standard 180 m at the sea level? Anybody in standard unit?
2116.
2116.2 or something. 2116.2 pound force per foot square. 2116.2 pound per foot square. Minus, oh, this is measured at 2070 pound foot square. Okay, so this is the density, 0.0024, which we assume constant, drugs per cubic foot. If you punch the number, you get 244.972 feet per second. By the way, do you need to take a notes for this kind of crap? I don't know. Are you taking notes for this crap? I hope not. You don't need to take any notes for this stupid crap. This is a bird is doing. I'm not doing this. But anyways. So this is miles per hour wise. This is 167.026 miles per hour. Here, my job is done. Do you think so?
No.
Any question or any comments? Go ahead.
Don't you have to make sure that
You have to make sure
the
that.
Mach number is under 0.3?
That's one thing. Anybody else? Go ahead.
It has to be incompressible, also steady. Well, it's already steady since we've gone from 3 screens.
So I hope you are going through already those kind of limitations that you can use Bernoulli. In other words, without going through this step-by-step process to confirm if you can do this, this is plug and check, and I'm not interested. Like I said in last class, plug and check can be done by anybody. So your job as an engineer is you make sure double check going through this limitations to use Bernoulli to begin with. First of all, is this steady flow? Like Robert said, this is probably steady because you're seeing streamlines. Of course, yeah. Okay. Number 2, nobody falls. Is it true? Because this is wind tunnel. Maybe? I don't know. Do you think this is wind tunnel? No one says that. This is probably actual flight. And then somebody actually cares about how heavy your air today is? No. So that means, hey, nobody falls. This is aerodynamics. Okay, check mark. Oh, if the viscosity is ignored, do you think so? You can never ignore such a thing, but in this particular case, can you treat this as an outside of boundary layer type of location? In other words, exactly how close this point A is from the surface. If it's on the surface, of course, it's inside of boundary layer. Can you apply this equation? Yes or no? Probably not. Or maybe low speed, you can possibly ignore the effects of boundary layer. It depends on how you measure, what you measure also. So those are the kind of things you have to be very carefully, first of all, going through it. Then, and only then, what is Mach number here? That is the check mark Dylan wanted to say. What is the Mach number here? So again, it depends on your altitude. If this is the sea level, we're assuming sea level, right? Yeah, so this is the sea level standard day. Temperature is also sea level. That means you have a speed of sound 760 miles per hour. If it's a standard day on the sea level. This is 100 miles per hour. So somebody please pick up your calculator, punch the number 100 divided by 760. What's the Mach number? If it's sea level standard day. Somebody please, well, everybody, don't you have a calculator bringing with you? Go ahead, get busy. Calculate something.
0.13.
0.13. Everybody, from now on, bring your calculator. Punch the numbers in the class. What are you sitting here? So Mach number is 0.113. Huh. Okay. So this is based on here, though. Okay. So how can you tell this location is still less than 0.3? That's another question.
Yeah.
You have to double check after you did this. So this is 167.026 miles per hour. If this is standard sea level divided by 760, what's the Mach number then?
0.22.
0.22. Ooh. Ooh. Phew. You're okay. Suppose if this is 0.301, you go like, wait a second, right? So that's today's subject. So there's a limitation for Bernoulli, okay? You clearly realize it. You cannot casually pick up Bernoulli and do everything on it. You have to always double check before you even pick up and use. Go through the checklist, and after you complete your work, double check your Mach number at your exit. Go ahead.
So if the Mach number was greater than 0.3, now what?
Now what? You can never use Bernoulli. Well, maybe you can still use it, assuming that the professor don't catch you.
But
What? Go ahead.
So if it was above, would we be given temperature? Because that would, then we could dictate what the speed of sound was, and then we
Possibly. Wait and see. We're going to discover that in this chapter, okay? In this unit. So next page. Okay, so not really answering your question and making you feel kind of weird. Let's move on. Because you're going to discover, hopefully, by the end of this unit A3. Next page. Consider the same conversion that we did it, right? This is example AE301. We did it. So let's consider the same program. If the air pressure at the indent is P1, again, equal to 1 atm, what is the pressure at the exit? Then once again, Ernie bud pops up and start doing something. Then you kind of don't want to see this bud anymore, but this bud shows up and do something. Ernie thinks. And then, I'm not going to believe you anymore. But Ernie thinks, well, Ernie is like a typical Embry-Riddle student in your classmates here, You behave like that, right? You have to fix your behavior, right? Of course. Ernie thinks, So, well, this is better known. Rho 1 to P1 squared over 2 is equal to P2 plus rho 2 P2 squared over 2. Oh, wait a minute. What's rho 1 and rho 2? What are those? Rho 1 must be equal to rho 2. Otherwise, we can never use this equation. Density must be constant. So what kind of density do we use? Well, it says 1 atm. What's 1 atm? It depends. What's your altitude? Well, let's assume standard sea level. So that means P1 is 2116.2 10^4 feet square. Now, of course, you can get density rho 1. Standard sea level density is 1.225 kilogram per cubic meters. You can get this value, right? Do you know what I'm talking about? Where did you get this value? Not the Google.
Memory.
No, you can't memorize those things. It's not your job. Where did you get this information? Go ahead, tell me.
U.S. Standard Atmosphere Table.
Table. Where did you find it? It's a handout. Right?
Yeah.
Right? Yeah. Don't Google, though. It's not Google. It's a handout. Okay, anyways. Yeah, go ahead there.
I was gonna ask, it uses SI units in A3- or A301.
Oh,
so
that's right. This is what? This
yeah,
is SI.
P1 is equal to
I
2116
know.
pounds.
This is probably, yeah. So let's pick up SI unit pressure. How's that? SI unit wise, what is the standard sea level 1 atm?
1,325 Pascal.
300 what?
325 or 300.
325 Pascal, Newton per meter square. That's right. So 101 kilopascal. So okay. So this is density 1.225 kilogram per meter cube. That's right. Rho 1 is equal to rho 2, so this is 1.325 kilogram per cubic meter, assuming this is sea level, standard. Now, if it's assuming standard sea level atmospheric temperature also, you can say speed of sound is 320 meters per second. So if you divide 20, okay, so 20 meters per second in, 25 meters per second out.
Okay.
Go ahead.
Isn't the speed of sound at sea level 343 meters per second?
Something like that, 300 something. I don't remember.
Yeah, it's 340.
340?
343.
340, 340. Okay, I thought 320, but anyway.
I think that might be
Something like that. Yeah, I have to look it up.
Because if you use your A equation, the A equals square root of 1.4 times R times
If you're given
C,
temperature, yes.
it gives around 340.
Yeah, I believe you. So something like 340. So 20 divided by 340 and 25 divided by 340 is both way less than 0.3 Mach number. So let's go ahead and use Bernoulli. That's what Ernie thinks. Okay? So what is P2 then? So P1 plus rho over 2. What rho? Well, rho 1 is equal to rho 2. P1 square minus P2 square is equal to P1 is 1.01325 times 10 to 5. This is a Newton per meter square plus 1.225. This is like what kilogram per cubic meters over 2. And this is a 20 meter per second square minus 25 meter per second square. This is 1.0116 times 10 to 5 Newton per meter square. This is, oh, wait a minute. What's the difference between in and out? Almost negligibly small. This is always the case of low speed wind tunnel. You are dealing with small, tiny change of pressure over the surface because it's low speed. How do you pick up that kind of pressure? Do you have any idea?
Yeah.
Have you ever visited wind tunnel? Well, let's just go visit today. Go ahead, questions.
Can you go back really quick?
Go ahead.
I'm
Okay.
good, sorry.
Can you go back really quick to the slide?
You don't need to take notes for this. I mean, this is like, yeah, plug and chug. Ronnie did it. Even the bird, mascot bird can do this. Okay, anyways. So let's take a look at, can I go?
Yeah.
Okay. So let's just visit wind tunnel wrap today. ERAU wind tunnel wrap. Question here. What's this? This is a gauge, pressure gauge. 0 is kind of awkwardly right here. This is 0. Okay. So if this gauge goes this side, it is going to read off PSI. What's that? Pounds per square inch. Yeah, sure. If this gauge goes this way,
Vacuum pressure in mercury in inches of mercury.
this is vacuum. Inch of Hg. What the heck is that? 0.5 subdivision. So if this one goes here, this is 10 inch Hg back. Can you get absolute pressure from that reading right now, right here? Pop quiz.
Conversion to
How can you convert? Do you know how to convert?
I know that one
Well,
atmosphere.
tell me how to convert then. You don't have to do the pop quiz now, but tell me how to convert this into actual PSI. Is it plus or minus? Is it gauge or absolute? What is it?
your PSI gauge or your PSI absolute.
This is the gauge value, right?
Yeah.
Yes.
Minus.
So it's going to be minus value, right? Yeah. Measured from standard atmosphere, zero gauge. So this is going to be minus value comes up. And then inch Hg. So you have to multiply by the density of water, multiply by the Sg of Hg, which is 13.6. Multiply that, you get actual pressure. Make sure you go back to fluid mechanics and understand how to do it. I'm not going to cover that. I mean, this is fluid mechanics. Go ahead.
So why does the dial go and measure pressure in one direction
Yeah.
in PSI? And
Because this is a tank, you can use it in both ways. You can pressurize the tank, or you can make it vacuum tank. This is a high-speed wind tunnel. This is basically when you create the supersonic speed, you create a huge tank, make a vacuum, and suck the air right in really quick, and then create supersonic speed. You can visit supersonic wind tunnel, go step outside, you can see huge sand. That's a vacuum tank. Ooh, what's this? This is blowdown wind tunnel. That's the subject you're working on right now, quiz 3 or quiz 0 program 3, either way. You have to understand how this thing operates based on entirety Bernoulli's equation, because this is low speed. No matter how push up and crank up your speed is, this is going to go less than 0.3 Mach number. This is low speed wind tunnel. And then what are those things connected on the model? What is manometer, by the way? Why do you need to use manometer?
So measuring the pressure across the wing.
Yeah. But can't you use like a pressure gauge like this?
That interrupts the flow.
Why not?
It would impede the flow. You want something that doesn't.
Well, this is a pressure gauge.
You want it on the
Why do you
surface
use the tube and then filled with liquid and all that?
You want it on the surface of the wing because the
You
sensors
can
under
still put
pressure-
on the surface of the wing, connected the other side's mechanical pressure gauge. Can't you do that? Why not? If not.
You're looking for really precise measurements.
That's right. Because mechanical gauge needs to have a force to push some spring, then create some force, then measure that pressure out of it. You need to have certain magnitude. I mean, like you saw in the previous examples, what is the pressure difference
Tiny.
between here and low speed? It's so tiny. How can you pick up that kind of tiny pressure difference? This is the only device you can do. Manometer. Manometer has been covered in fluid mechanics. Do you really understand why manometer is used? This is the time. Manometer comes in with meaning. You have to use that for small, tiny pressure measurement. That's what you did. That's what you do in wind tunnel. That's why you use manometer. Okay. So, what's this? Pirostatic tube. What are you measuring? You're measuring airspeed. Well, by the way, we're going to revisit this one in Unit A4, airspeed measurement. So let's just stop here. So I'm gonna show you only two things. Okay. So let's just talk a little bit about wind tunnel, since you're working on quiz 3. Okay. So let's just take a look at the early bird flying in air. Well, this is a real thing. Early bird is moving. Air is not moving. This is the reality, right? Airplane's flying. Do you think air is moving? No, air is not moving. Airplane's moving. What's that? It's called dynamics. Okay? But you can never analyze anything in this. Because this is essentially, when you create this, this is going to create differential equation. Equation motion, differential equation. Hey, let's just pick up differential equation, plug in the value, get the number out. You can never do such a thing. So somebody needs to convert this into here. Let's say, imagine yourself, Ernie is not moving at all in air, but air is blowing with the same speed as if he is moving in non-moving air. Do you know what I'm talking about? Those two are the same or different?
Same.
Equivalent, I would say.
Yeah.
Something made you equivalent from here to here. What something? Something is involved to make an equivalent situation so that now you can analyze. What is it?
Is it because since the model staying still?
This is the Reynolds transport server. That's the whole point of taking fluid mechanics. Now you are going to employ the equivalent, which is airplanes in reality moving in non-moving air. However, you can never do any analysis. Everything is second order nonlinear partial differential equation. Okay, so now you're going to employ the idea of control volume. This is the control volume. You see that? There is a control volume. Now within that, air is incoming, and you are not moving. Right?
Right.
So now you can, okay, so you can do something. So right here, what is the pressure? Gauge, in terms of gauge, 0. 0 gauge. So right here is the stagnation point of Ernie. What is the pressure? Huh? Huh?
Stagnation?
Is it the same pressure here?
No.
Is it higher or lower?
Higher.
Higher. How much higher?
V square over 2G.
Ooh, that's Q.
Ah.
Q is 1/2 rho V squared. Dynamic pressure, isn't it?
Yeah.
So this is essentially dynamic pressure. This bird is feeding. So if this bird is moving really fast, you're feeding high pressure here and here and here. Why is that? Because you're moving faster and faster. Higher dynamic pressure starts to hit in here. That's called also total pressure or stagnation pressure at the same time. So you can say here. So what's this gauge pressure here?
0.
0. How about stagnation point here? Q. Huh. So those two are equivalent. Very similar, or I can almost say same. Now here's a question. So this is something you really need to think about as you try to work on quiz 3 or quiz 0 problem 3, either way. Now anybody is sitting inside a wind tunnel. Is this exact same thing? Close, but no. How can you say that?
Because density is, well, it's in an incompressible flow. So density is constant.
Yeah, density is constant, low speed.
Yeah.
Yeah, it's the same. Anybody, please make a comment.
And then you have a test stand fixture in there as well. That takes up some of the data.
Yeah, let's just ignore that kind of stuff too.
Okay.
Other than that, something is fundamentally different. If so, what is fundamentally different from here to the other two?
The boundaries of the other two are infinite, and this one has 2 boundaries.
Let's ignore that too. Something more fundamentally very different. Yeah,
This isn't necessarily free stream. Like,
this is free stream.
Is it,
we can assume free stream.
Yeah, this is free stream. It's the same velocity here.
is it scale modeling?
Yeah, scale modeling. Well, yeah, it's the same thing. Well, you can stick actual Bruni in it. Go ahead.
Because the velocity can go so much greater.
Yeah, what?
You can have such a greater velocity and you could have the
Well, velocity is the same. Let's assume that this velocity v is the same as if Ernie is flying, same velocity. Anybody else? Go ahead.
Does it have to do with right things?
No. Move on.
It's a controlled environment.
Control the environment. Yeah, but move on. Something is fundamentally very different. No one knows.
Free stream.
Okay. So I have a question here. Let's take a look at. Let's take a look at the quiz 3. Oh, actually, quiz 0. I don't want to touch quiz 3 because it's your work. So quiz 0, problem 3. Let's take a look at it. Okay. So lots of people try to solve this problem using Bernoulli's equation. Yeah, of course. Sure, you can. But here is one important thing. If you apply Bernoulli's equation, show me the streamline that you are applying the equation with. Otherwise, I'm not going to give you any partial credit. It's fundamentally terribly wrong. You apply, casually pick up Bernoulli and then apply in any location you want to, but where is the streamline? If you don't show streamline, it's invalid. So let's draw streamline. That's the first step. I'm going to draw streamline just like this. This is a streamline. Right here is really far away. Okay, this is really far away from this wind tunnel, but anyways, something starts moving from here. Velocity here, what's the velocity? About 0. Not quite, because it starts moving here. What is the pressure here in terms of gauge? 0 gauge, it's atmospheric. So this one slowly pick up the speed along this streamline, pick up a speed along this streamline, and sucked right into the wind tunnel becomes velocity v right here. Velocity is v. Okay?
Mm-hmm.
Then burn hits in front of the car, velocity is 0, stagnation point. This is velocity about 0, pressure is 0. what is the pressure here where the velocity is 0?
Dynamic pressure.
Huh?
Your dynamic pressure.
Yeah, dynamic pressure is, what is dynamic pressure? Dynamic pressure is 0 because it's not moving. It's the stagnation point. What is the pressure? Pressure is 0, right? Right? So this is the velocity v here. So what is the pressure here? There.
It's going to be dynamic. No, if it's the same streamline, it's 0.
Wouldn't it be,
0?
No,
wouldn't it be negative dynamic pressure?
Oh. Speak up.
Negative dynamic pressure?
One more time.
Negative dynamic pressure?
Is that what you're saying? Cool. Why is that? You guys think about it. You're applying Bernoulli's equation along a given streamline and trying to figure out what is the static pressure at each location based on the velocity. Right? If the velocity is 0, static pressure is 0, total pressure is 0. In other words, P plus Q is 0. That's what you're talking about, right?
Yes.
Yeah. Yeah. This is static pressure. This is dynamic pressure. If you add them together, it must be always 0 along this streamline. So right here, if the Q is 0, P must be also 0. Right here, same. If the velocity is 0, Q is also 0. Well, P is, wait. If the velocity is 0, Q is 0, that means P is also 0. Right here, velocity is B. What is P equal to?
Minus Q.
Minus 1/2 rho B squared. That's right. Negative Q. So this is how this blow-down wind tunnel operates. By turning the fan, you create a vacuum inside of the wind tunnel that draws the air in. So what is the highest possible pressure inside of the wind tunnel?
Minus Q.
0. 0, of course, because that's the total pressure you can produce. No matter where you go, total pressure is 0 along this streamline. Right here happen to be very low pressure of static. That is going to induce the dynamic pressure, which means you produce the airspeed. So this is the trade-off between flow energy to the kinetic energy. Think about those things, very fundamental, because people use Bernoulli without knowing what they're doing. Okay?
Yes.
Important. So have a great weekend and return in quiz 3 on Monday. If on it. Okay? Okay, so let me stop recording.